can solve. We can solve and get that this is A times 1, 1 transpose for any non-zero A is an eigenvector for lambda equal to -1. Okay. Similarly, for lambda equal to 2, any scalar multiple of the vector 5, 2 is an eigenvector. Okay. So there are two directions. 1, 1 is one direction. Okay. And 5, 2 is another direction. 5, 2 is another direction. 5, 2 is another direction. So there are two directions in the plane, so that this matrix A, the matrix A is a transforming vectors from R2 to R2. So it says that when I think of the function which is induced by A, the linear transformation which is induced by A from R2 to R2, then this line is mapped to itself. And this line passing through 5, 2 is also mapped to itself. And these are the only two lines which are mapped to themselves. There are no other lines which are mapped to themselves. Okay? Yeah. So the direction of the lines which are mapped to themselves, these are called the eigenvectors, and the scaling factor is the eigenvalue. Okay. So for the coupled system of differential equations, we reduce the problem to finding lambda so that Ax equal to lambda x, and we solve this. We solve this. This turned out to be first eigenvector. This turned out to be second eigenvector. So ut is equal to e to the power minus t, t equal to -1, lambda is equal to -1. So e to the power lambda t times yz. This is e to the power lambda t, lambda equal to 2 times yz. And so therefore these are the functions. V equal to, so V equal to e to the power minus t and plus 5 e to the power 2. Okay. So if u1 and u2, this will give rise to solutions. U1 and u2 are solutions of differential equations. Then their sum is also a solution. And there you can take scalar multiple of u1 and u2. They will also be solutions. So this is one solution. I multiply by C1. This is another solution. I multiply by C2. Then this is also a solution of the same coupled system of differential equations where lambda 1 equal to -1 and lambda 2. Okay, and C1 and C2 are arbitrary real numbers. X1 is any eigenvector for lambda 1. X2 is any eigenvector for lambda. So we started with a coupled system of differential equations of order 1 where two functions are involved, and we reduced this to problem to finding eigenvalues and eigenvectors of the coefficient matrix, and then we found the general solution of this differential equation, right? So the parameters C1 and C2 I can find by simply putting t equal to 0. So u of 0 is equal to C1 x1 plus C2 x2. X1 and x2 are eigenvectors, and u0 I know. U0 comes from the initial conditions. Initial conditions were v0. Yeah, v0 was correct. V0. Yeah, V0 is 8 and W0 is 5. So you keep that in mind to find C1 and C2. Yeah. So putting t equal to 0, we will get V0 and V1, which are known to us. Yeah, the parameters C1 and C2 can be found by using initial conditions V0 equal to 8 and W0 equal to 5. And this will give me C1 and C2, and therefore we have found all the solutions of the differential equation. Okay, so this is interesting. A problem which is arising in differential equations is reduced to a problem about solving simultaneous linear equations and finding eigenvalues and eigenvectors of a 2x2 matrix. And you can imagine now this can be done if you have n ordinary differential equations with n functions, I can set up a n by n coefficient matrix and guess the solutions and find out the eigenvalues and eigenvectors of an n by n matrix. Yeah, but the catch is that when we find the characteristic polynomial, it's a degree n polynomial. So the problem remains a nonlinear problem. Yeah? Finding eigenvalues, eigenvectors is a nonlinear problem, and it is amounting to finding roots of a degree n polynomial. Finding roots of degree n polynomial is a complicated problem because for quadratic and cubics we can solve. For quartic equations also we have exact formula for solutions, but beyond the quartic equations we have to use numerical methods to find out the roots. Okay, so there are very effective methods to find out the eigenvalues and eigenvectors, and in practice they work. Yeah, although we find approximate eigenvalues and eigenvectors, but in practice they do give us whatever we say. Yeah, so let me define rigorously now. I have been talking a bit loose about eigenvalues and eigenvectors. Let me define rigorously what it is. So our field of scalars has to be fixed in order to fix a vector space. So suppose field of scalars is R or field of scalars is C. Field of scalars could be other fields also, like field of rational numbers. Okay, but you fixed a field of scalars, and then we talk about matrices where the entries are in this field of scalars, and then we define eigenvalues and eigenvectors of linear operators also. Okay, so let V be a vector space and T from V to be a linear operator. So it's a linear transformation from V to V. Then we say it's a linear operator. Yeah, the field of scalars is fixed. A scalar in the field of scalars that is said to be eigenvalue of this linear transformation if there is a vector V, so that TV equal to lambda V. This is exactly same as finding AX equal to lambda X. Yeah, if we are given a matrix A is give rise to a linear transformation TA from R2 to R2, so it's a linear operator from R2 to R2, and finding this X means finding a vector in R2 so that TV equal to lambda V. So the one-dimensional space which is passing through V is mapped to itself because V is mapped to lambda V. Right? Every vector on this linear span of V is mapped to its constant multiple lambda V. So the one-dimensional space is mapped to itself. There is a scaling factor lambda. So this lambda is called the eigenvector, eigenvalue, and V is called an eigenvector of this linear transformation. And keep in mind that the scalar has to be taken from the field of scalars. So you may have real matrix like we came across. Sometimes we come across a 2 by 2 real matrix, and then this real matrix gives rise to a characteristic polynomial which has no real solutions. Then we cannot say that this matrix has eigenvalues. Eigenvalues, if we are working with real matrices and our field of scalars is real, then the eigenvalues have to be real, because we have to find out vectors in R2, okay, which are mapped to a scalar multiple. But if lambda is not real, I can't get lambda V to be a real vector. Okay, so that's why lambda has to be in the field of scalars, and V is called eigenvector with eigenvalue lambda. So suppose I take a matrix, n by n matrix over the field of scalars, then an eigenvalue and eigenvector of this matrix is the eigenvalue and eigenvector of a linear map from Fn to Fn, which is induced by this matrix TAV equal to AV. Yeah, V map to A times V. V is a column vector. This is a column vector in Fn. AV is a column vector in Fn. So this linear transformation may have some eigenvalues and eigenvectors, and then we say that these are the eigenvalues and eigenvectors of A. So we have now moved from eigenvalues and eigenvectors of matrices to those of linear transformation, and eigenvalues of eigenvectors of matrices are a special case of eigenvalues and eigenvectors of linear transformation. Linear transformation is defined on any matrix, any vector space V. The vector space may be a vector space of functions. It may be a vector space of matrices. Yeah, but then the concept of eigenvalue is the same as we defined for matrices. It is copied from the definition of eigenmatrices, that the eigenvalues have to be always in the field of scalars. Okay, and TV equal to lambda. Okay, TV equal to lambda v may have no solution. A given linear operator may have no eigenvalue. We will see exactly. But if there is eigenvalue, then we can reduce the problem of finding eigenvalues and eigenvectors of a linear transformation to that of a matrix. We can convert the problem of finding eigenvalues, eigenvectors of a linear transformation to those of finding eigenvalues, eigenvectors of matrices. So the fundamental problem remains the same. Given a n by n matrix, how to find its eigenvalues and eigenvectors. Yeah, eigenvectors have to be non-zero. Column vectors in Fn, AV equal to lambda v. Yeah. So let V be a real vector space. Suppose I take a real vector space of all smooth real valued functions. Smooth means every derivative exists. All nth derivative exist for all n, like the exponential function or sine x function or cosine x function. These are smooth functions. They have derivatives of every possible order. So look at the real vector space of smooth real valued functions. Okay, and on this vector space of smooth real valued functions, I applied the derivation d over dx. This is the usual derivative of a function, and derivative of a function which is smooth is taken to a smooth function. Yeah, its derivative will also be a smooth function. So we start with this matrix and we end, a vector space of smooth functions. We end in the same vector space of smooth functions. So in order to define eigenvectors and eigenvalues, we must have a linear operator. The derivative function is a linear transformation. Yeah, but you see, we know that derivative of e to the power lambda x is lambda times e to the power lambda x. So lambda is an eigenvalue and e to the power lambda x is eigenvector. Yeah, because this is my function. This is the element of the vector space. E to the power lambda x is the function, and it is being multiplied by lambda under the action of this linear transformation, which is differentiation. Differentiation is a linear map from v to v, and it maps this function to a scalar multiple of this function. Yeah? So, but this is a non-zero function. E to the power lambda x is a non-zero function. So this function e to the power lambda x is an eigenvector with eigenvalue lambda. Okay. Yeah. So this is the new interpretation of exponential functions, that they are eigenvectors with eigenvalue lambda of the differentiation operator acting on the vector space of smooth real valued functions. Okay. Yeah, let's take a diagonal matrix with scalars lambda 1, lambda mu 1, mu n on the diagonal, and then we will have this notation for diagonal matrix DIAG mu 1, mu 2, mu n. This is a good notation for a matrix whose diagonal entries are mu 1, mu 2, mu n, and other entries are all 0. Okay, so let us understand what is the meaning of eigenvalues and eigenvectors of a diagonal matrix. So if I have this diagonal matrix, then let me take a simple example, lambda mu, this diagonal matrix. Yeah? Then when I apply this on the first basis vector 1, 0, I get the first column vector. This is lambda 0, and this is lambda times E1. And the same diagonal matrix, if I apply to E2, then it is equal to mu E2. So lambda is an eigenvalue, E1 is eigenvector, mu is an eigenvalue, E2 is eigenvector. Okay, so eigenvalues turned out to be the diagonal entries of this diagonal matrix. Okay, so if I have diagonal matrix, then I see immediately what the eigenvalues are, and that is because eigenvalues are roots of the characteristic polynomial a minus lambda x. A minus lambda I, sorry, a minus lambda I. Okay, this is n by n matrix, and this is this determinant. What is this determinant? This is equal to determinant of a equal to mu 1, mu 2, mu n minus lambda, 0, 0. Determinant of a diagonal matrix is the product of its diagonal entries. Mu 2 minus lambda, mu n minus lambda, and characteristic polynomial is this. And so this says that lambda equal to mu1 or mu n. So the diagonal entries are the eigenvalues, and the corresponding eigenvectors are the standard basis vectors. These are the eigenvectors. Okay. Yeah. So now suppose I have a linear operator from a vector space and lambda is a scalar. Then look at all vectors so that TV is equal to lambda v. Every vector v so that TV is lambda v, and lambda is fixed. Okay, lambda is fixed. So if I take two vectors which satisfy this equation, T u equal to lambda u, then the sum also satisfies the same equation because T is a linear transformation. So u plus v is also satisfying the same equation, but u plus v could be zero vector. Yeah, u and v could be non-zero, but u plus v can be zero vector if v equal to minus v. But look at all the vectors, okay, which are solutions of this equation. So v could be zero. Zero vector goes to zero. So zero vector certainly belongs to this set v lambda. But whenever v is non-zero vector, it is an eigenvector with eigenvalue lambda. So look at the linear span of all the eigenvectors of a fixed eigenvalue lambda. This is called eigenspace of lambda. This is subspace of V. Okay, V is my big vector space. V is my big vector space on which my linear transformation is acting, and inside this vector space, I have corresponding to each eigenvalue, I have a subspace. V1 lambda 1, EV lambda 2, etc. If my linear transformation is acting on a n-dimensional vector space, then there will be at most n eigenvalues because they are roots of a characteristic polynomial of degree n. And for each eigenvalue, I have this vector space of all vectors so that TV is equal to lambda v. This is called the eigenspace of lambda. Lambda is an eigenvalue of T, and V lambda, any non-zero vector in V lambda is an eigenvector of T with eigenvalue lambda. This is called eigenspace. Yeah. So with every eigenvalue, I associate an eigenspace. So if T was, if this T was coming from a matrix, if this linear transformation is induced by a matrix, this linear transformation is induced by a matrix, yeah, then A u equal to lambda u, and suppose lambda is in F, then u is an eigenvector, and V lambda is eigenspace. And we know that it is consisting of all the vectors so that A minus lambda I u equal to 0. And therefore, eigenspace is simply the null space. Okay, it is the null space of the matrix A minus lambda I. Okay, the eigenspace is the null space of the matrix A minus lambda I. If it contains a non-zero vector, then we say eigenspace is the null space of A minus lambda I. Okay, so A minus lambda I is another matrix. It's a n by n matrix. Lambda is the unknown quantity. Suppose I know this lambda, that there is an eigenvector corresponding to lambda, then its null space of A minus lambda I is precisely the eigenspace V lambda. So I can find out the eigenspace simply by solving the equations. This is a homogeneous system of linear equations. Once I know lambda, I look at this homogeneous system of linear equations, solve for all the x's. They go into V lambda. That is the eigenspace corresponding to lambda. So for every eigenvalue, I have an eigenspace associated to it. Okay. So suppose lambda 1, lambda n are scalars, and suppose they are distinct eigenvalues. Yeah? They are distinct eigenvalues. So I go to the characteristic polynomial and find out the roots of the characteristic polynomial and check whether they are in the field of scalars. And suppose lambda 1, lambda 2, lambda n are distinct roots of the characteristic polynomial and they are in the field of scalars, then once lambda i's are eigenvalues, there will be corresponding eigenvectors, and they will be non-zero eigenvectors. So this theorem says that if I pick up eigenvector corresponding to distinct eigenvalues, then these eigenvectors are linearly independent. Eigenvectors of distinct eigenvalues are always linearly independent. This is very important observation. So we find by solving the characteristic polynomial, we find the eigenvalues in the field of scalars. For each eigenvalue, I have an eigenvector. That eigenvector lives inside the eigenspace. Okay, there are n distinct eigenvalues, and these n distinct eigenvalues, they give rise to eigenspaces v lambda 1, v lambda 2, v lambda n. Okay, let us see that there is nothing common between them. Yeah, there is nothing common. Only the zero vector can be common between any two of them. How? Because suppose AV equal to lambda 1v, and this v is in the same eigenspaces v lambda 1, v lambda 2, then AV is equal to lambda 2. Okay, so that says that AV, if I subtract, then what do I get? Left hand side becomes 0, the right hand side becomes lambda 1 minus 2 times v, but v is a non-zero vector, and this lambda 1 minus lambda 2 is non-zero. This cannot be 0. Non-zero vector times a non-zero scalar cannot be 0 vector. So therefore, v has to be 0. So eigenspaces, any two eigenspaces, v lambda 1 and v lambda 2, they intersect only in the 0 vector. Okay, and so by the formula we proved for sum of dimension of the sum of two vector spaces, it says that if I add two vector spaces, then the dimension of the sum is equal to sum of the dimensions v lambda 2. Okay, so let us prove this fact. Keep that in mind, that two eigenspaces corresponding to distinct eigenvalues have only the 0 vector in common. Okay, now let's prove this fact that if I take distinct eigenvectors corresponding to distinct eigenvalues,